All right, so here's another example. Same idea as the previous case. Just wanted to get one more under our belts. So we have a different vector field and a different surface. Here's the vector field that we're given. And the surface S is defined to be the boundary of the solid enclosed by the cylinder x squared plus y squared equals 4, and the planes z equals y minus 2 and z equals 0. We want to find the flux of F across S. So the first thing I'd probably want to do is see what this region looks like once we graph it. So go like this, z, y, x. So we're talking about a cylinder. X squared plus y squared equals 4. So I know that we're looking at a circle of radius 2 in the xy plane. 2, 2. That's going to determine this cylinder. And then the plane z equals y minus 2, the trace of that plane in the yz plane would look like, let's go like this, -2. It would look like a line of slope 1 and y-intercept, or z-intercept of -2. So what this is going to do, if you take this thing and cut this cylinder, it's going to slice off a chunk down there. I never draw this very well, but hopefully it gives you sort of a sense of that. So this is what roughly what our cylinder is going to look like. Now, I'm going to use the divergence theorem to turn the surface integral that gives us the flux across this boundary into a triple integral over the solid region that's enclosed by this boundary, which we call E. Now, anticipating that, I know that in evaluating this triple integral, the region or the solid looks like a cylinder that's been sliced. That to me makes me think that it's going to be easier to evaluate that triple integral using cylindrical coordinates as opposed to what we were able to do in the last video, which was just do it directly as was. So I am going to begin by describing this region in cylindrical coordinates, r, theta, z. Okay. Now, r theta, remember we can think of r theta as basically like polar coordinates in the xy plane. And if I look at the cylinder in the xy plane, this thing is a circle of radius 2. So that means r is going to be between 0 and 2. Theta is going to be between 0 and 2 pi. And what about z? Well, z is bounded by a top surface and a bottom surface, and we have equations for those surfaces. The equation for the bottom surface is z equals y minus 2. However, remember, we're converting things into polar coordinates, so I have to make a conversion with that y. I can't use y in my representation of this solid in cylindrical coordinates. Remember, y is equal to r sine of theta. So really, this bottom surface can be thought of as z equals r sine of theta minus 2. That's less than z, which is less than the top surface, z equals 0. Okay? That's what I'm going to end up using when I convert to cylindrical coordinates in my triple integral. I also know that I'm going to need the divergence of f. Now here's the beautiful thing. When you take the divergence of this vector field, right now the vector field looks very complicated. Once I do the divergence, it becomes so much simpler. So what is the divergence of f? Well, differentiate with respect to x first. That's going to give me y plus 2z. Y plus 2z. Plus, differentiate with respect to y here. That goes to 0, and then I get a 2y right there. Differentiate with respect to z. I get negative 2z. That whole thing goes to 0. So minus 2z. 2z and minus 2z cancel out. Y plus 2y is 3y. My integrand became massively simpler looking. So now let's use the divergence theorem to evaluate this flux. What I'm looking for is the flux of f across s, which is what this surface integral is, by the divergence theorem. That's equal to the triple integral over E of the divergence of f. Okay. Now I'm going to write this out explicitly. What is it that we're actually taking the triple integral of? Well, first of all, remember I'm making a conversion into cylindrical coordinates. So this is going to become the triple integral from, I'm going from 0 to 2 pi here for my theta, 0 to 2 for my r, and then r sine of theta minus 2 to 0 for my z. And then my integrand becomes 3y. However, remember, we need to convert this to cylindrical coordinates. So instead of 3y, I'm actually going to be writing 3r sine of theta. Now remember, when you convert to cylindrical coordinates, the Jacobian here is r. So I have to make sure and include that r. This is going to be dz, dr, d theta here. Okay. So let's begin with the inner integral. Notice dz is the only thing with a z in it. So this becomes integral from 0 to 2 pi, integral from 0 to 2 of 3r, let's put the z here, sine of theta, from 0 to r sine of theta minus 2 dr d theta. Now I can see when I plug the 0 in, the whole thing goes to 0. So I'm going to have the z is going to become minus this times 3r sine of theta. What I'm going to do is use the minus that's going to occur from this to just switch the order of the subtraction here. So really what this turns into is the integral from 0 to 2 pi, integral from 0 to 2 of 3r sine of theta 2 minus r sine of theta. Oh, actually, I'm realizing I left something important off here. Let's do this. This r here, I'm going to multiply it to this r here. That becomes r squared. Don't want to forget about that, making this an r squared as well. Okay, so now I have this dr d theta here. Let's go ahead and distribute. So I'm going to have integral from 0 to 2 pi, integral from 0 to 2 of, okay, so if I multiply, I'm going to get, let's actually bring the 3 out of the integral completely because it's a constant. It can be, we could do that. I'm going to have 2r squared sine of theta minus r cubed sine squared of theta dr d theta. Okay. Now let's see. I know that I'm integrating with respect to r next, so let's deal with that. 3 integral from 0 to 2 pi. This will become 2/3 r cubed sine of theta minus 1/4 r to the 4th sine squared of theta. Now I know that I'm anticipating having to integrate. Actually, no. You know, I'm getting too far ahead of myself. So I don't really need those parentheses there. But this was with respect to r, and we're going from 0 to 2. Okay, so this will be equal to 3 times, now let's see. So when I plug in a 0, everything goes to 0. That's all going to go away. R cubed, 2 cubed would be 8, so that becomes 16/3 sine of theta. 2 to the 4th will be 16 divided by 4, that's minus 4. Okay, here's where I'm going to make this this change. So I know that sine squared, in order to do the integral here, I want to use a reduction formula. This is equal to 1/2 sine, or 1 minus cosine of 2 theta. Okay, d theta. From here, 0 to 2 pi, we can represent this as 16/3 sine of theta minus 1/4 times 1/2 would be 2, so it's -2 times 1, so that's just -2. -2 times negative cosine of 2 theta, that would be plus cosine, plus 2 cosine of 2 theta d theta. This gives me 3 times, this is going to look like -16/3 cosine of theta minus 2 theta plus sine of 2 theta from 0 to 2 pi. Now, when I evaluate cosine of theta, 0 and 2 pi are coterminal to each other. So cosine of 2 pi and cosine of 0, same with sine of, it would become 4 pi here, 2 times that, and sine of 0. These are going to end up canceling themselves out when I plug these in, which means the -2 theta is the only thing that matters. Plugging a 0 in gives me a 0, so really it's just plugging a 2 pi in here. This becomes -4 pi times 3, which is -12 pi. Okay? Now I want to give sort of an interpretation of what it is that we're getting here. So in the previous example that I did, we had, let's see, it was, which one was that? This guy. So in this example, we used the divergence theorem to find the flux of this vector field across the boundary S. What do we interpret that to mean? So if you think of the vector field as a fluid flow, water, air, whatever, electrical charge, that kind of stuff, the flux you can think of as like net flux. The fact that this is positive means that in the grand scheme of things, you have more fluid flowing out of this surface than flowing into it. Okay, whereas here we ended up with a negative result. Make sure I write negative there. Which means here, if I were to have drawn the vector field, all the vectors pointing, whichever direction they're pointing, you would have more fluid flowing into this surface than out of it. That's what the negative result means. So, can we use the divergence theorem and this idea of flux to give a better interpretation of what divergence actually means? Well, yes. And I did talk about this interpretation back when we introduced divergence back in section 16.5, I guess it was. But this is where we can make that a little bit more concrete. So what I'm going to do is say that V of xyz is going to be a velocity field of a fluid flow. And we're going to assume constant density rho. Okay, this is going to look kind of similar to what we did when we talked about the interpretation for curl in section 16.8, where we talked about Stokes Theorem. Okay, then F, if we define a vector field F as the scalar constant rho times the velocity field V, that would represent the rate of flow per unit area. Just physically, that's what that would mean. Now, if I let P naught be some point in the fluid flow, and I put a small little ball around P naught, I'm going to call the ball BA, and A is going to be the radius of the ball, and it's centered at that point, B naught. And we want to think of A as being very, very small. Now, in a fluid flow, the fluid flow itself would be continuous. It'd have continuous partial derivatives. That's just from the physical nature of this thing. The divergence would then be continuous as well. And remember, just like when we talked about the curl in the last section, when you have a function that's continuous, what that means is that small changes in your inputs correspond to very small changes in your outputs, or relatively small changes in your outputs. Because the ball BA is considered to be very small, then if I choose some other point in that ball, which I just call P, and evaluate its divergence compared to the divergence of our vector field at the point P naught, the center of the ball, we should expect a very, very little change from here to here. So I could say that these two things are approximately equal to each other. And this will be true for every P in that little ball B of A. Now, if we let S of A be the sphere that's acting as the boundary of B of A, what I can do is approximate the flux of F across that surface, that boundary surface, using the divergence theorem. So according to our divergence theorem, the flux of F across S of A will be equal to the triple integral over the ball B of A of the divergence of F. But using our approximation, remember this B of A, all of the points within B of A are their divergence is approximately the same as the divergence of F at that single point at the center of the ball. Because I'm using a single point here, this is a constant now. So this can be brought out of the integral, and now I'm looking at the triple integral of dv over the ball B sub A. And remember, when you have a triple integral of the form, or with an integrand that's just equal to dv, then what the result is the volume of that ball. So I end up with the divergence of V at P naught times the volume of the ball. Okay. Now, again, intuitively, we expect the approximation here to get better and better as A shrinks down to 0, because that's shrinking that ball down more and more, which means these points P are going to be brought closer and closer to P naught, improving this approximation here. So if I solve this for the divergence of F at P naught by dividing both sides by the volume of the ball here, and then if I take the limit as A goes to 0, I expect this approximation to become perfect. And again, think about what that would mean. That ball is going to be shrinking down to that center point. So this intuitively would make sense. How then do we interpret that? Well, remember, this is a flux integral, and we're dividing it by volume. So what that is giving me is the net outward flux. Remember, because it's a positively oriented surface, so we interpret it as outward. The net outward flux of F at a point now. In the limiting case, this surface shrinks down to just a single point. So we interpret the divergence of F at the point P naught as the net outward flux of F at the point P naught. And if the divergence of F is positive, that means that your flow, the fluid flow is moving closer to parallel to the unit normal of this vector here, which basically, and because this is oriented outwards, we interpret that as meaning that the net flow is outward near that point. And in those cases, we refer to P naught as a source. I've talked about that when we talked about divergence back in 16.5. And intuitively, you can think of it as a tiny little pipe at the point P naught, causing the fluid to flow outward from that point. It's providing, fluid. That's technically not what's happening there, because we're not assuming that fluid is being added to the surface at P naught. It just helps kind of make a little bit more of a physical analogy to think about. If the divergence at that point is negative, then that means the fluid is acting opposite to the direction of the outward unit normal. So we expect fluid to be flowing inward toward that point. In those cases, we call P naught a sink. Again, if you imagine a fluid flow, and we're going to talk about this one here, if you imagine a tiny little drain at that point, then the fluid will flow toward that drain because it wants to sink into that drain. So that's why we call that a sink. Okay. So we're going to do an example where we're just sort of eyeballing it. We're not working with a vector field that's given to us explicitly, at least the way that I stated this. We just need to take a look at what's happening near a couple of points with our vector field. So this is classify the points P1 and P2 in the vector field shown below as sources or sinks. Now, because I don't know what the vector field is, I can't use this, I can't find the divergence of it directly, right? But I can look at what's happening near these points with this vector field. So let's start with P1. If you pay close attention to the point P1, the vectors are kind of flowing toward P1 if they're coming from here, and away from P1 as you get, further north and west, I guess. Take a look at some of the vectors that are near P1. This vector here is close to, it looks like it's flowing into P1 or very close to it. And remember, this vector field is made up of more vectors than what we see here. These are just representative vectors because you can't draw all of them. There's infinitely many. So there's going to be other vectors that are doing pretty much the same thing as this one, just very close to it. That means these smaller vectors are flowing into P1. And then you have larger vectors flowing out of P1 here. Notice they're coming out of this little area surrounding P1. So what does that mean for the net flux of this vector field near this point P1? Well, the net flux, there's a small amount flowing in, but a larger amount flowing out. So taking the net of that, we would expect the combined action of this to be giving us more fluid flowing out of P1 than flowing in. That would make P1 a source. So P1 is a source here. Okay, take a look at P2. We actually see the opposite thing happening. Here's the vector field, and if I look below P2, I see longer vectors that seem to be pointing towards P2. That means they're flowing into P2. And I see smaller vectors flowing out or away from the point P2. So there is more fluid flowing in to this point, or the small region surrounding that point, than there is fluid flowing away from it. That would make P2 a sink. Okay, so you notice we're eyeballing it, but we can make that determination based off of what we're seeing around those points. I would expect then the divergence of this vector field at P1 to be positive and the divergence of this vector field at P2 to be negative, because that's what would give us these things, sources and sinks, conclusively. Okay, that's essentially it for section 16.9. The last thing I want to do is what's technically called 16.10 in your book. It's a summary of a lot of results that we've encountered up until this point. And it's showing a sort of unity amongst these 5 really, really important theorems in calculus, beginning with the fundamental theorem of calculus. And then the remaining 4 are all theorems that we covered in chapter 16. So we have fundamental theorem for line integrals, Green's theorem, Stokes theorem, divergence theorem. There is a commonality in all of these. And in a certain sense, you can actually think of every single one of these theorems as a special case of Stokes theorem. There's a way to show that this can kind of lead to all of these. Really, it's better if you work with the most general case of Stokes theorem to show that, like I had mentioned in the last section. So here's the commonality. First of all, in every one of these integrals, we're taking an integral of something that you can think of as a sort of derivative. So notice here, capital F is the antiderivative of f prime. So I'm taking the definite integral of f prime. Here, the line integral, this is from the fundamental theorem of line integrals, I'm taking the line integral of a gradient of a function. Well, remember, a gradient is a kind of like a type of derivative of a vector, right? You take partial derivatives of the components of that vector. Here, in Green's theorem, I'm evaluating a double integral of something that resembles, derivatives. There's partial derivatives here. Partial of q with respect to x minus partial of p with respect to y. Stokes theorem, I'm taking a surface integral of the curl of f. The curl, remember, that's del cross f. Del, again, is a differential operator. So this is kind of like a derivative of sorts of the vector field f. Here, the divergence theorem, the triple integral that shows up there involves the divergence of f. Remember, that's del dot f. Again, del, the differential operator del. So in all 5 of these cases, the thing that we're integrating is some kind of a derivative of a function. Now, what's happening on the right-hand side? Well, on the right-hand side, in each one of these, we see the function that was whose derivative was taken in the integrand. So if I have capital F prime here, in the fundamental theorem of calculus, we have f showing up on the right-hand side. Same thing here. Del f. F is showing up, remember, f is like the potential function, given that this would be a conservative vector field. F is showing up on the right-hand side. Similarly here, partial of P, partial of Q, I get P and Q showing up here. Curl of F, I get F showing up here. Divergence of F, I get F showing up here. Not only that, what are we doing with those functions? Well, we're evaluating those functions along the boundary of whatever set we were integrating over in the first place. So what do I mean by that? In the case of a definite integral, we integrate along intervals from a to b, a to b. I can think of the endpoints of this interval as the points a and b, which are exactly the points that we're using on the right-hand side here to evaluate that definite integral. Okay? Same thing is happening here. Remember, R is the parametrization of the curve C. And in the case of the fundamental theorem for line integrals, the curve C that we're integrating across is a curve, but f of R of B minus f of R of A is the endpoints of that curve. So we can evaluate the integral along this entire curve simply by using the endpoints with this antiderivative of sorts. Green's theorem is actually doing the same thing. We're integrating over a plane region, D, but we turn that thing into a line integral of functions that, in a sense, are antiderivatives of this, along the boundary of that region D. The boundary in this case, though, doesn't look like a couple of points. It looks like a closed curve. What about Stokes' theorem? Same thing. We're doing a surface integral, but remember, in Stokes' theorem, we don't assume that this surface is a closed surface. So it has a curve that acts as its boundary. C is what we call that. The boundary of our surface S is C, and I can evaluate this surface integral over S by simply using a line integral over its boundary. It gives me the same thing. Divergence theorem, the last one we just talked about. We have a solid region enclosed by a closed surface S. If I want to evaluate a triple integral of this function here over this solid region E, then all I need to do is take a surface integral of the surface that encloses it. So I don't need to use anything interior to that solid. I can actually evaluate it by only using the surface on the outside. That common thread that's happening with integrals here is not a coincidence. Like I said before, you can actually show that all of these follow from Stokes' theorem. And if you look at the general version of Stokes' theorem, which is beyond the scope of this class, it's differential geometry, it gives kind of this unifying theme to all of these results that we seemed to have come up with from different places. In fact, it turns out to, if you know the language of differential geometry, it makes it a lot easier to prove all of these than the way that we proved them. But that is something that is the best way to wrap up this course, I think, is to draw those parallels to kind of help you see that, again, none of this is coincidence. The commonality in these results is all coming from somewhere. Okay, so hopefully that made sense, and that's going to wrap up section 16.9 and the course for us.